Hello, everyone, and welcome to our Black Hole Apocalypse panel. It is 1 o'clock, however, I'm going to give folks a couple extra minutes to filter in, so we'll get started right about 1:02, 1:03. So we're going to give folks a few more minutes to join, because I know everyone is just coming from their lunch sessions. If you're joining now, you'll see that I did just start a poll to see just about how many of us got a chance to watch the documentary prior to today. If you didn't get a chance, no worries whatsoever. We'll be talking about a lot of stuff, and so this conversation will still be something that can be really valuable regardless of whether or not you had the chance to watch it. But just if you get a chance, please let us know if you watched it already, so we get a sense of how many folks have seen it versus who's coming in kind of newer. So with that, we'll take a couple minutes here and get started very soon. Thank you. I had one question just come in for the link to the documentary, so I just shared that in the chat panel. Note that it's a 2-hour documentary, so you're not going to be able to watch it right now if you haven't gotten the chance. But for those of you who are wondering how to access it, it is free on PBS and can be accessed at this link. It is also available on Netflix. Okay, we're going to do about 1 more minute. I still see folks filtering in here, so another minute before we get started. Okay, we're going to go ahead and begin. Thank you all so much for joining us back this afternoon. I know we've had a lot of astronomy outreach happening today, a lot of different new science concepts, so I'm really excited to still have so many of you with us to learn about black holes. I'm really excited about this event, and I think that we'll have a really great discussion. So again, my name is Voelker, and I'm our coordinator of outreach programs. And today I am joined by 3 faculty members who specialize in black hole research. I'm going to go ahead and let them each introduce themselves and tell you a little bit about the work they do. So with that, let's start with our vice chair of the department, Professor Todd Thompson.
Hi, everyone. Thank you very much for being here. It's a pleasure to get to talk to you today. I am vice chair in the Department of Astronomy and professor there, and I'm a theoretical astrophysicist. So that means I do a lot of interpreting of observations that observational astronomers make. Particularly, I focus on the physics of supernova explosions and neutron star formation and black holes, how black holes form in the centers of massive stars when they collapse. And I also work on the origin of the elements, how massive elements like uranium and platinum and gold are produced in those events. And last year we had a big press release because we discovered a candidate black hole binary system where a black hole and a star are orbiting each other in the outer galaxy that we got some press about. So this is an interesting topic to me, and I hope it is for you too.
Thank you so much. Next, I'd like to have Smita Mathur, Professor Smita Mathur, introduce herself.
Hello, everybody. Nice to have you around, and it's fun. We did I finally did watch the movie last night, so I know it's what it's all about. It's kind of things that we do teach in actually our introductory astronomy classes. So any younger people out there, if you want to take any of these classes, you would be most welcome. I have been working on observational aspects of black holes for many decades. And if you have watched the movie, then I can use the words used in there, I suppose. So I observed the supermassives, as it was called in there, the black holes which are millions to billions solar masses. So those are the kind of black holes that I study.
Great, thank you. And last but not least, we have Professor Laura Lopez.
Hi, thank you for joining. So my name is Laura Lopez. I'm an assistant professor in the astronomy department here at Ohio State. I study the birth and death of stars, so how stars are born from collecting gas together, and then also how they die once they run out of their nuclear fuel, and sometimes they lead to black holes. And so I use observations. I use the entire electromagnetic spectrum, but I do tend to focus a bit on X-ray observations. So those are high energy observations using space-based telescopes to study these extreme events like those that produce the black holes, and many of the ways that we find black holes, as was discussed in the documentary, is using these X-ray facilities.
Great, thank you. So I'm going to go ahead and get started with some questions of my own that I prepared for us all today. But if you have questions at any time, please feel free to submit them via the Q&A chat feature, and this will help us make sure that your question doesn't get lost in the regular chat. So use the Q&A to submit questions at any point during the conversation, and we'll be sure to ask those to our panelists. So first off, I'll start with Laura, since you spoke last. For those who maybe didn't get to see the documentary, could you give us just a brief introductory definition for what is a black hole? You know, why are we all here today for this talk to begin with?
Yeah, sure. So yes, the documentary is about black holes. I thought it was a really great documentary, very, very informative, covered lots of bases. And it talked about these extreme objects that we now have confirmation that they exist. They are produced at the end of a star's life when sort of runs out of its nuclear fuel in the core can't support itself anymore, and it implodes. And if it's massive enough, if the star's mass is more than 8 times the mass of the sun, then it can keep imploding. And if it's even more massive enough, it'll implode down to a single point. All that mass will go into what we call a black hole. It's a black hole because not even light can escape, and you end up with these very extreme objects that are very tiny in size. All their mass is in a single point, but they have masses that are many times the mass of the sun. And so, as the documentary discussed, we have black holes that are produced by the ends of stars' lives, that are stellar black holes. We also have supermassive black holes, which are millions or billion times the mass of the sun, and those tend to be at the centers of galaxies. And there's a lot of debate about where those actually come from, how you can get something so big.
Amazing, thank you. And that's a debate we're definitely going to dive into during this panel. But first, I wanted to just start with some more basic questions that I had from watching the documentary. One of the quotes was, "A black hole is a place where there's nothing except gravity." But this really threw me because, as you just mentioned, black holes seem to have something. Like you said, up to billions of times the mass of the sun. So are we talking about a place where there's nothing, or is there really a whole lot of something? Which one is it?
There is a whole lot of something. And Todd, if you want to chime
Go
in.
ahead.
You could, but black holes definitely have a mass. So it is not nothing. In some rare circumstances, even that mass can even evaporate. I don't want to go there at all, but there is definitely something. And at the same time, it is reasonable also to say that there is nothing, in the sense that all you feel is the gravity of the black hole, and you don't really see anything, which is why if you see, as it was shown in the documentary, if you see the stars going around and you see it is going around what, and you see they are really going around nothing. There is nothing at the point around which all the other stars are going around, or the binaries system which was shown, like you see a star going around a point, but what is there at that point? And there is nothing. I think it's in that sense they've meant nothing, not really in the sense of void, perhaps.
Yeah. Thank you. That's really helpful. So you did mention gravity, and one of the things I thought was interesting was they talk about Einstein's conception is that there are no forces anymore, just objects curving space-time. So my question for you then is, why do we all still call it the force of gravity? Are we, you know, if we're talking about how Einstein says there's no forces, just curvature of space-time, why are we calling that the force of gravity?
I think we can think about it both ways. I think the Newtonian sense, in Newton's sense of a force acting on something, we do feel forces, and those can be real things, regardless of whether or not you know, it's actually being caused by the curvature of space-time or something else. In this case, it is easiest in Einstein's theory to think about the force of gravity as being due to this curvature of space-time, which they tried to demonstrate with this so-called rubber sheet analogy, where you put in a big mass and it deforms the rubber sheet, and that's why marbles, you know, roll around on your deformed rubber sheet. It's a good way to think about it. It's a good mental picture. At the same time, you know, gravitating bodies interact with each other, and they interact with each other by warping space-time, but also we can say by exchanging gravitons, which is a more quantum way to talk about the gravitational force. And so I think we can talk about those things in multiple different ways, depending on what we want to convey about the thing we're talking about and in which physical regime we want to talk about it.
Thank you. Excellent. One of the big statements that I wrote down from the documentary was the quote that time will become so slow for you when you are falling into a black hole that you will watch the entire universe unfold before your eyes. I think we just need to talk about that. That's a really big thing to say, and I'm going to need you guys to help me unpack that statement. Am I really going to watch the entirety of the universe unfold before me if I have the unlucky fate of falling into a black hole?
So I don't think so. I think that that's not right. I think that when Neil deGrasse Tyson says that, he's incorrect. I think the reason he says that is because we have this thing which we can get into about time dilation and relative frames, about if you're very close to a black hole and very far from a black hole, you'll perceive time running differently. And there is a real sense, if you from some minimum safe distance tossed me into a black hole, you would see me, my actions, and whatever timekeeping device you have to keep track of me, you would see me slow down as I approach this point of no return we call the event horizon. And you would eventually see me essentially stop and sort of wink out of existence very near the event horizon. And that formally, in some senses, you would never see me actually cross the event horizon, and I would appear to freeze, you know, as I'm falling in. And that leads to the idea, which is often mentioned, and which Neil deGrasse Tyson mentions, that as that was happening to me, since I'm freezing from one perspective, I would then see the entire future of the universe. That's where that general misconception comes from. But that's not actually true. As I'm falling in, we talk about a thing called proper time, which is defined locally as you're sliding down this incredibly curved space-time. And in that frame, if I was just looking at my watch, I'd be like, oh, 1, 2, 3, 4, 5 seconds would be clicking by. And it is true, the whole universe would become quite distorted, and there would be some strange effects, but I would not see the rest of future history pass. I don't have access to that. We have words that we use to describe that, like it's not in my light cone. But what it means is that there are certain parts of the universe and certain parts of future that are inaccessible to me as an observer as I slide through that event horizon. So I think what he meant is not correct.
Thank you. Laura, Smita, do you agree with that?
Yes, we do. I mean, I think the first part of that statement was kind of correct in the sense, just the way somebody far away would see the falling in person, Todd, in this case, being slow. Todd might see you being faster. So that's just a reflection of one to the other. But the other thing, like you're seeing the future unfold between you, it was, that's not correct at all. Yeah.
Thank you. And so if Todd is falling into the black hole, you mentioned that you'd be frozen there. Would you be frozen for infinity, or would we eventually see you disappear? So does your image go away at some point in time?
You want to answer that one, Smita?
Yeah, go ahead. You will disappear, I think.
Yeah, so that's right. So, I mean, it depends on what when we talk about viewing something, what do we mean? We talk about detecting photons from it. So right now you're detecting photons from my face, which are being reflected from sunlight and ambient light and then transmitted through these intertubes to your eyeballs. And so, you can imagine illuminating me as I'm falling towards the black hole, or you can imagine me firing a laser at you. If I'm firing a laser at you, you will see the laser or any illuminating thing that you're trying to, reflect off my face so that you can view me. You will see the amplitude of that light decrease and decrease and decrease, and it will get stretched. It will be redshifted to longer and longer and longer wavelengths. And so you will effectively see me disappear from the electromagnetic spectrum, because I will be sort of infinitely redshifted and infinitely the more or less infinitely redshifted, and time will become infinitely long relative to me. And so then that sense, I will freeze, but I will also disappear, because I will just become redder until I'm no longer perceptible by you, is one way to think about it. But for me, I'll just go right through. And my watch will keep ticking 1 second at a time.
Wow.
As I go through the event horizon.
Thank you. So the next question I have is sort of about the starting size a star needs to be. So at one point in the documentary, they mentioned that a star needs to be about 10 solar masses to become a black hole. And then later on, when we're talking about a specific instance, they discuss Cygnus X1, and how key to this argument was that Cygnus X1 had to be at least 3 solar masses. So I'm wondering if you all can please talk a little bit about this sort of starting solar mass number. Why at one point are we talking about 3 solar masses for Cygnus X1, and then at another point we're talking about a general number of 10 for all starting masses for stars?
Laura,
yes, I can do this. Yeah, so in general, stars, their masses, their total mass is what determines the fate, but then what becomes a neutron star or black hole tends to be the core of the star, and other than that, the rest of the star can actually explode or be ejected, and you can lose that mass. And so your starting point is this larger value, and it's actually debated what mass you need to be in order to produce a black hole. I think the way that we teach it in our introductory astronomy classes, we say that perhaps something like 8 to 20 solar masses would produce a neutron star, and 20 and up would produce a black hole. But that's actually debated and a big area of research here at Ohio State to try to figure out, what mass stars lead to neutron stars versus black holes. But however, you have that total mass, but then the core is the part of the star that implodes. And how far that implosion occurs depends on the mass of that part of the star. If you have, not very much mass, if you have less mass than 1.4 times the mass of the sun, then you'll end up with what's called a white dwarf, something that is that mass but is the size of the Earth. If you are a bit more, then you can implode further and you end up with something that is maybe 2 times the mass of the sun in the size of Columbus. And then if you're even more, then about 3 times the mass of the sun, then you actually keep imploding. It cannot support itself, and it leads to a black hole. So the object that's left over, if it's more than 3 times the mass of the sun and we can't see it, then it is a black hole. So that's sort of the limits that we look for, and that's why they were able to show that Cygnus X1 was likely a black hole, was because this unseen mass that a star was orbiting was more massive than could be supported.
Thank you so much. So I am getting a couple questions from our audience members. So we're going to break here for our first round of audience questions. So the first question is, can you elaborate on the debate over the origin of these supermassive black holes at the center of galaxies? So they mentioned here that Laura referred to this in the beginning, and this is something that we can definitely go into. I have a lot of questions on this as well. But if you could talk a little bit more about this debate about the supermassive black holes. Why is this complicated?
Go ahead, Smita.
Yeah, so what Laura talked about is what we call the stellar black holes, right? So these are the end products of stars. So they have masses, as we said, for Cygnus X1, you mentioned, Anna, so it had like 3 solar masses, or it would be few solar masses, few tenths of solar masses. Those are the kind of masses we understand as end product of a life, of a star, a very massive star dies, and we make these what we call stellar masses because they are the end products of the star's life. But then at the centers of the galaxies, we have these supermassive black holes, which are millions to billions times the mass of the sun. They cannot possibly be produced by stars. So these are not stellar black holes. They are not produced by stars. And therefore, the question is, how did they form? And there are multiple pathways for growing these black holes to these huge, humongous values that are actually measured. One of the things is just by eating the gas around you. So this is what we call accretion of gas onto the black holes. This was also discussed in the movie. And if you keep eating mass like this, so which is for active galaxies and quasars, which is of the order of 1 solar mass a year, and if you eat it for 1 million years, then you can have 1 million solar masses. So that's one pathway of becoming so fat. And other way is that you can have the merger of smaller black holes. So let's say you start with several thousand solar masses, and then you keep merging them, so then you double the mass, and you merge those and you double the mass, and you still keep growing like this. So that's another pathway. But even then, if you find very, very high mass black holes very, very early on in the history of the universe, which is what we call at high redshift, then neither of these scenarios seem to be working very well. And this is where the active part of current research comes in, as to how to make these black holes so big, so early in the life of the universe, in the history of the universe. And this is when the direct collapse of gas clouds was invoked as one of the solutions for this thing. And so, and how do you find, I mean, even if these black holes grew by merging together, how did the seeds form? That was also a question. And even those seeds would have to form by just direct collapse of gas clouds, possibly at the same time when the galaxy itself formed. Like, as we said, these supermassive black holes are at the centers of galaxies, and galaxies have to form some way, and maybe the nuclear black holes also formed at the same time.
Thank you. And I'm really glad you mentioned this idea of direct collapse, because that's something that I thought was a really interesting point in the film, where they talk about having these large gas clouds collapse themselves into the black holes. And so one question I have, they talk about the reason we think this has to be is because that there's simply a speed limit for how fast a black hole can eat and grow. And since we see these black holes early on, we know that there has to be a different way for this to be happening. So I'm wondering if you guys can talk a little bit about the speed limit. They refer to it as the Eddington limit, and they say that light has a pressure. Photons can import a force on something. We see this in winds from stars. Light is pushing out gas. So there's a limit on how fast you can feed a black hole before its own light quenches its growth. So I'm wondering if you can talk a little bit more about that concept. I think it's something that's pretty complex, and they sort of breeze over in the film, and I'd love to delve a little bit deeper into that idea.
Todd, do you want to go?
I can go. There are a couple concepts that sometimes get confused. So I'm gonna try to be very careful about what I say. So when these black holes are accreting, they give off light, and the reason they give off light is because stuff gets hot. And when stuff gets hot, it radiates. That's it. So anything hot, the Earth, Laura's cat, me, whatever, those things are radiating photons. Everything's radiating photons. Stars are radiating lots of photons because they're hot. And then when the gas is accreting on the black hole, it radiates energy because it's hot. So, and it is absolutely true that light has a pressure and it's pushing on everything. It's just that for our daily lives, that's very small because we're not being illuminated with the light from a trillion suns. If we were, then maybe we would feel that. So as this gas is coming in, if you take a bunch of gas moving towards a black hole and you shine a light outwards, you'll find this critical limit to the luminosity from the black hole. That is this Eddington limit. It says that if a black hole is radiating more than this Eddington limit, then all the gas would fly away. And if it's radiating less, then it would fall in. Okay, so the limit is usually the limit. They mixed up a couple things here because they were saying that the limit is on the amount it can eat. It actually turns out that if you force feed a black hole somehow, if you very rapidly were able to get a bunch of gas in and around the black hole rapidly, then you could actually beat this limit. And it's easy to beat that limit because that happens whenever you form a black hole in the center of a star. As Laura was describing, whenever that happens, it forms and the gas is rushing in at way, way, way above the Eddington limit, like 10 to the 7 times above the Eddington limit. So you can beat the Eddington limit. It's just that it requires very extreme circumstances to beat the Eddington limit for a supermassive black hole in a galaxy. That requires very strange gas conditions, almost as strange as those direct collapse gas conditions. So really, the limit is on the luminosity. The black hole shouldn't be shining at very much above the Eddington limit, but it could, because we're still trying to understand exactly how black holes radiate when they're being fed very strongly and when they're in different regimes. It just turns out that black holes shine differently when they're way above and way below this critical value of the Eddington limit. But their implication that you can't grow a black hole above that limit is formally not right. It's just this luminosity threshold. So you have to be a little careful. That's a very active topic of research. In fact, Smita has studied super Eddington accretion on black holes, and I've looked at it theoretically. So it's a thing. That's a thing. Yeah.
Great, thank you. That's really fascinating to know. So talking about these supermassive black holes, I want to learn more about if they really are in every galaxy. Is that what we think? Why do we think that? And if we say every galaxy, do we only mean spirals, or are we including all of the irregulars, ellipticals, everything? So could you tell me a little bit more about just how many galaxies do we think have these supermassive black holes in the center?
So the current thinking is that practically all practically, I think I had to put qualifiers in here because really you can always point me to some galaxy and say, oh, but no, that one doesn't have one. So I'm going to put these qualifiers here. But the current thinking is that practically all galaxies contain a supermassive black holes in their center. And that includes the elliptical galaxies, the giant elliptical galaxies, spiral galaxies, at least some fraction of dwarf galaxies. Whether irregular galaxies have them, I do not know. That is the case. Our own Magellanic Clouds, which are irregular, small galaxies, I do not know whether they have a supermassive black hole in their center. I do not think so. So that's why I had wanted to put that qualifier there, that not all galaxies, but the current thinking is that generally most of the galaxies have supermassive black holes in their center.
Do we think that literally all of the spiral ones do, or is there still a qualifier there that there might be some, perfectly standard spirals that for some reason or another do not have it in the center?
So that's a good question. People, because for practically every galaxy people looked at, they found the supermassive black hole in it, one can extrapolate and say that, it must be therefore the case that really all spiral galaxies do. But have we really found one in each of those galaxies? The answer is no. We haven't really found one in each of the spiral galaxies. But if you extrapolate from what we know, then maybe they could.
I think the one that is most surprising to me that doesn't have one, and Todd and Smita can jump in, is I think M33 does not have one that's been found, and they have and that's a spiral galaxy, and they have strict limits on it, and they haven't found one. But that's the only one I know of that kind of is an oddball.
Yeah, I think one of the examples they use in the movie was the great Andromeda galaxy, the sister galaxy, the Milky Way, and they said that it had a very massive supermassive black hole in its center, and they pointed to that one, and that's a great example. But literally, the galaxy next door is this M33 that Laura just mentioned, which is also called Triangulum, and you could Google it, or I could bring up a picture, but very pretty spiral galaxy that notably does not have the central sphere of stars. Many spiral galaxies have a central sphere of stars we call the bulge. And M33, this Triangulum galaxy, has almost no central sphere of stars, and people have been hunting, trying to find a supermassive black hole there. And if somebody does find one, then it will make worldwide news, because it's something that astronomers are very keen on for precisely this reason.
Amazing. Thank you so much. So I do have some new questions from our audience, so we're going to break again to have some of their questions answered. So first is from Barbara, who mentions that the film talks about the event horizon where everything disappears. Is this also the Schwarzschild limit? What is that? So could you talk a little bit more about the Schwarzschild limit mentioned and what that actually means?
So the event horizon is what we consider the radius of the black hole, and what determines that is the mass at the center, but ultimately it is where the escape velocity from the black hole equals the speed of light. And what that means is anything interior to that radius cannot escape, including light. And anything outside that radius, if it moves really fast, it can still get away, but it has to move really fast. And so in general, this is called the Schwarzschild radius. So when people talk about the event horizon, they're talking about this Schwarzschild radius, which is just set by, again, where the escape velocity is the speed of light. Yep.
Great, thank you. So the next question is back to the person falling into a black hole. As one passes through the event horizon along the way, at what point will you begin to actually experience the stretching and eventually be torn apart?
It depends on the mass of the black hole. If we had a little bitty black hole right here, right next to my head, my nose would be pulled more strongly than the back of my head. And what that would do would cause a tidal distortion, and my head would undergo what's called spaghettification. For low mass, stellar mass black holes, like a 10 solar mass black hole, like the black hole in Cygnus X1, they said was about 15 solar masses. If you were falling on a radial trajectory towards that black hole, so the tidal force would significantly overwhelm your body strength, and you would succumb before you ever got to the event horizon. You would be several hundred kilometers, maybe 1,000 kilometers for a 15 solar mass black hole. I'm trying to do the calculation fast, and you would die before you ever got to the event horizon. However, if you went to a supermassive black hole, like a billion solar mass supermassive black hole, you would go through the event horizon without feeling anything. And the reason is because all of that mass is located in the singularity, and the event horizon is big for a supermassive black hole. And so when you're out here at the event horizon, you're safe because the singularity is far away, and so you could travel much closer. And so the thing to figure out is whether or not the local acceleration from those tides is bigger or stronger than a couple g, because you can stand maybe at 5g or something, maybe 10g in a pinch, no pun intended. And then so that's what it is. So a supermassive black hole, you'd make it almost to the singularity, and a low mass black hole, you would die outside.
So you're telling me if I was told I had to be murdered by a black hole and I had no choice, but they did let me pick which black hole, I'd be safer picking a bigger one.
Also, yeah, and it'd be a longer trip too, so you'd get more time to think about it. So I would prefer the supermassive black hole. Absolutely.
So now all our viewers know that very specific piece of information. If you're
That's right. It could come in handy. You never know.
You know which black hole to choose as your murder. So we do have a hand raised here from Haley. So Haley, I'm going to go ahead and hit allow to talk. And when you get a chance, you can unmute yourself and ask your question.
Hi. So I wanted to ask you, if you technically had a black hole above your head, wouldn't gravity stop you from going through that black hole? I mean, because gravity is the one keeping you on the ground, right? So
you mean if there was a black hole like above me right now?
Yeah.
Then yes, if there was a black hole and we oriented its mass correctly and its distance correctly, then in principle I could kind of levitate between the black hole and the Earth, because that's right. So you would feel the collective effects of all the gravity right now. So in fact, even the sun is pulling on you, but it's just small compared to the gravity of the Earth. The Jupiter is pulling on you, but it's small compared to the gravity of the Earth. The moon is pulling on you, but it's small compared to the gravity of the Earth. So if something big compared to the gravity of the Earth, equal to the gravity of Earth, were situated just perfectly, then yes, you could make yourself levitate. Mm-hmm.
Whoa. Okay.
Yeah. Great question. Thank you, Haley. I really like that. So I now have one from Ben, who asks, it is thought that the Milky Way has absorbed several dwarf galaxies in its history. Did those dwarf galaxies have massive black holes? And do those black holes still exist in the Milky Way now? Great question, Ben.
So, could be true that Milky Way has merged with several other dwarf galaxies from the neighborhood, and it is possible that those dwarfs had black holes at the center. We do not know, but all of those would have merged onto the supermassive black hole, which is a million solar mass, a few million solar mass supermassive black hole at the center of our Milky Way. So right now we do not have evidence of other black holes around the central black hole. So if those other galaxies had a black hole, they would have by now merged, because we don't have evidence of multiple black holes at the center of our galaxy.
Great, thank you.
And we do have, we also see some galaxies are kind of being shredded and being in the process of being merged with our galaxy, like the Sagittarius stream and things like that, we do not have any evidence of a supermassive black hole in them. So it is possible that the dwarfs that merged with our Milky Way either had supermassive black holes or they did.
So when it comes to supermassive black holes within our galaxy, we only know of one, and it's at the center. Is that correct?
That's correct.
When we're talking about regular stellar mass sized black holes, how many do we have evidence for within our galaxy?
We have evidence for dozens, I would say, in our Milky Way galaxy, because our primary way to find them is from them accreting material from a star orbiting them. And so we can look for that signature. However, if there's an isolated black hole, we have no really way of seeing it. And then that being said, given our expectations of what mass stars produce black holes, we do, and how many stars there are in the Milky Way, we think that there are probably 70 million black holes, stellar mass black holes in the Milky Way. So there are a lot, and we've only found a very, very tiny amount of them.
Amazing. And do we think that this idea of, tens of millions is sort of standard in other galaxies too? So when we look at the universe as a whole, do astronomers have a prediction for how many black holes we theorize to be out there?
Yep. Yes, I think our Milky Way is pretty standard. And so if there's 100 billion galaxies, then there should be,
18.
Yeah, 10 to the 18 black holes in the universe. Wow. 10 to the 18 power.
Wow, so we're talking about 18 zeros right now.
Correct.
Yeah.
So that's a lot of black holes, yes. So we have a couple more questions here for you guys. And this one's a little bit more general, but I like it. It has some capital letters, a lot of enthusiasm. I have to ask, is it actually reasonable for us to think we could live in outer space? What do you think?
Sorry, can you repeat the question?
Yes, the question asker says, I have to ask, capital letters, is it actually reasonable for us to think that we could live in space?
Oh, like empty space? No, but in a space shuttle, yes.
Yeah. So, and I will add to that too, one of the goals right now for NASA in particular is trying to make places like Mars habitable. So when we're talking about living in space, other places in space, definitely. But yes, we need some type of habitat for ourselves to survive. So great. So the next question is, would it be possible for these stellar mass black holes and galaxies to account for dark matter?
It's a great question. People have had that question, and we're very interested in that black holes could do that. And there are still tiny regions of parameter space where it might be allowed, tiny, but for the most part, the resounding answer to your question is no, it doesn't. And we know that because of experiments that were done. One was called Macho, and there were others where basically they just stared at this dwarf galaxy that was already mentioned called the Large Magellanic Cloud, and they looked at it thousands and thousands and thousands of times, and what they were doing was looking at all the stars in the background, hoping that if black holes did make up the dark matter, then you would eventually see a black hole pass in front of one of those stars, because here's the galaxy, here's the dwarf galaxy. If you're staring at this, then there must be many black holes passing by. You would see one go by one of these stars, and you would see it brighten characteristically over a certain amount of time. And after years and years and years, astronomers are very patient, and taking many pictures, they found not enough such events to account for the dark matter. So short answer is, there are other arguments too, but that's the one people mostly cite. So it seems like no, black holes are not the dark matter.
Thank you. So another question here about terminology. So we have these terms quasar, active galactic nucleus, and black hole with an accretion disk. What is the difference between those three concepts?
practically nothing, but the different names have come, basically there are historic reasons for these different names. So the supermassive black holes which are accreting, that's the system that we really have. But how were they first discovered? They were first discovered in radio observations, and that's what was shown yesterday, that people wondered what are these star-like quasi-stellar radio sources. And so quasar is just mixing of those words, quasi-stellar radio sources, and therefore they got to be called quasars. And then, so this was, as I said, discovered in the radio band of the electromagnetic spectrum with big antennas. But then later people figured out that not all of these accreting supermassive black holes are really strongly emitting in the radio band. They are actually very nicely seen in optical, the light that we see. They're seen in ultraviolet, they're seen in X-rays. So different, so it is then becomes difficult to call them all quasars because the radio part is not there. And we also understood that all these accreting supermassive black holes are the centers of galaxies. Therefore, we started calling them active galactic nuclei, because then they are nuclei of galaxies. They're active in the sense that they're actually emitting light, so we see them. And so this is why all these different nomenclatures have come about for historic reasons. But they all refer to the same thing, that you have a supermassive black hole at the center of a galaxy which is accreting. So if there is a supermassive black hole at the center of the galaxy which is not accreting, if it is then quiet, then it is not active. And then we typically may not, then we wouldn't call them active. But the black hole may still exist.
Thank you. That's super enlightening. And as a follow-up to that, Barbara mentions that if quasars were discovered by radio astronomy, why would this discovery of quasars not be by X-ray, since they are so energetic? So why was it radio and not X-ray that made the discovery of quasars, is the question.
It is just timing. We did not have X-ray observing facilities. We had antennas for a long time, and especially the radio technology was really developed to its very high sensitivity, and the technique was in general developed greatly during World War II. And after World War II, when in peaceful time, people started looking up rather than Earth signals. And so radio astronomy really took off after World War II. But to observe X-rays, we cannot observe them from the ground, because the Earth's atmosphere absorbs X-rays coming from the outside of the universe. So definitely it absorbs X-rays coming from quasars. And therefore, to observe X-rays, you have to go above Earth's atmosphere. And that technology, development of technology took way longer.
Thank you. So next is a big question here. What is Hawking radiation? And as a follow-up to that, given Hawking radiation, what is the expected lifetime of a black hole?
Go Smita or Laura, or should I?
No one
You
wants-
go.
You can do it, Todd.
Yeah. Okay. So Hawking radiation. So the first thing that you should know is that Einstein's theory of gravity, general relativity, is what we call classical theory. And what that means is that it doesn't have any quantum mechanics in it. It's not a theory that's joined up with quantum mechanics, whereas all the particle physics, and sometimes you hear about it described as the standard model, and sometimes you hear about described as all these different forces, the electromagnetic force, the strong and weak nuclear forces, all of those are quantum mechanical theories of microscopic interactions. And Einstein's theory of general relativity kind of exists outside that. And there have been a bunch of investigations over time some by Smita's husband, who's one of the world's experts on this. That's why Samir Mathur, who's in the physics department, great guy, knows a lot about black holes, more than me. But he people have been working on different theories to unite general relativity and quantum mechanics. And one of those you hear about a lot is string theory. So sometimes if you watch PBS shows on string theory, they will talk about what's going on at the singularity, what's going on at the center. That's a bit beside the point. But the point is just to set things up, is that a lot of physicists have been working for a long time to try to unite concepts of quantum mechanics with concepts of general relativity. And one of the first breakthroughs or results from Hawking, and also related to stuff by a person named Bekenstein, was about how black holes might be able to radiate, because they're this interesting surface that exists in the quantum mechanical background of space-time. And that space-time is filled with quantum fluctuations. You can think about it like particles or quanta winking into and out of existence that forms a background in space-time. But now here you put in a boundary, some kind of interesting boundary, the event horizon. And what that allows is for certain types of these quanta, these particles or photons, to radiate from that surface. Because in a sense, this is not the best descriptor, but it's the one used by Hawking in his book, so maybe I should be able to use it too. But you can think of particle and antiparticles as being generated, and one kind of going into the black hole and one leaving, and that leads to a net radiation. It's not quite it, and you shouldn't really be thinking on a subatomic level. You should be thinking on the scale of the black hole itself, because the particles, the radiation that's produced by a black hole has a characteristic wavelength that's of order the size of the black hole, which for a 10 solar mass black hole is about 30 kilometers. And so that's what sets the size scale. And that's what Hawking radiation is. It's one of these fundamental things about putting a boundary, a causal boundary, in a quantum mechanical soup of particles winking into and out of existence, consequence of that. What is the expected lifetime of black hole? Very long. So for the supermassive black holes, I can't remember what the number is, but like 10 to the 90 times the age of the universe, or some for supermassive black holes. For stellar mass black holes, it's much more reasonable, like only 10 to the 55 times or 10 to the, I don't know, something like that, 10 to the 60 something years. And if we made a black hole out of something smaller, like me or you, I weigh, I don't know, 50 kilograms or something like that. 100 kilograms, how much do I weigh? I don't know, 200 pounds. Anyway, if I was a black hole, you'd have to shrink me down very small, but I would evaporate actually very rapidly. I can't remember the number there either, but a trillionth of a second, probably. Some number like that. So if you made me into a black hole, I would immediately evaporate, and I would evaporate into radiation. And it would be my rest mass energy. Which is enough to take out, if you just immediately converted me into energy, that would be enough to take out more than the city of Columbus, because E equals MC squared, and I'm a bunch of M, and C squared is a big number, makes a big E equals MC squared. And so if you did convert me to energy, it would be bad for everybody. So that's one of the reasons why we don't think that low mass black holes exist, because if you made a hypothesis, like I hypothesized that small black holes exist, we think that they would immediately evaporate. And if they evaporate on a time scale that was small compared to the age of the universe, then we would see those explosions all over the universe from evaporating black holes. And since we don't see them, we constrain the existence of such things.
Just one small thing to continue add to what Todd just mentioned is that age of the universe today, it's about 14 billion years. So what would be the mass of black holes that would be evaporating like about now? And that would be the mass of about Mount Everest.
Oh, nice. I didn't know that. Good.
Nice, yeah.
Mount Everest. Yeah.
So we have just a few more minutes here, and before we sign off, I did want to mention something that they covered at the end of the documentary, which is Ligo. So this seems to be a really important part of current black hole related research. And one of the things that I found very striking about this is that when they discovered this merger of two black holes, they mentioned that the power was 50 times stronger than the output of all the stars in our universe put together. So I think that any statement like that, I need you guys to talk to me about that. How can something, just one event, be 50 times more than everything else out there? If you can tell us a little bit more about this, why this discovery is significant, and what does LIGO mean for the future of black hole research?
I would let actually Todd talk about it, but I just wanted to say, Anna, that this is a great question, because when I heard that, I hadn't heard that before, that it is actually so. And so it did surprise me. So I did actually calculate how much it would be. And yes, that is about right. So I dropped all the factors of 2's and 5's and things like that. But yes, that's about correct. And so, yeah, so it was interesting that was one piece of information that I did learn something from watching.
Thank you for using your skills to verify it for us. So now I can believe it.
Yeah.
You want to go ahead, Laura?
No, you're good,
Answer
Todd.
part of it. So the luminosity thing is interesting. It is really interesting. So first of all, what's the total power output of the rest of the universe is an interesting place to start. And we already actually almost said it already, because we were doing the calculation. Laura was doing the calculation of all the galaxies, and she said there are about 100 billion galaxies, like the Milky Way, which is about right. Yeah, that's the number. And each of those big galaxies has about 100 billion stars. And each of those stars is, roughly speaking, for our purposes here, radiating with the luminosity of the sun. And so if you take 100 billion stars times 100 billion galaxies, that's 10 to the 22 stars. And each one is radiating with the sun's luminosity, which is this big number of watts or joules per second or ergs per second or whatever energy per second you want to radiate. So that's the number you want to get above, is 10 to the 22 stars. And it's interesting because black holes have this very particular size scale, the Schwarzschild radius, this event horizon. And that is their size scale, and that depends only on their mass. Okay. And so you have two black holes that are orbiting around each other. They have a mass, here's a mass, and they have an event horizon that's this size, and then they merge together when they get about this close. And what's neat about that is that the time for them once they coalesce, the amount of time it takes is just the amount of time for light to cross from one to the other. And that light crossing time is also the size of the black holes. And so what happens is that if you say, what's the characteristic luminosity, the total amount of energy that's going to be radiated divided by the total amount of time, you find this beautiful relationship, because the total amount of energy that's going to be radiated is proportional to mc squared, the mass times c squared of the black holes. And the amount of time that's going to be radiated over is the light crossing time between the two black holes, which is also proportional to the mass. And so you get a fundamental luminosity scale of the universe that has only to do with fundamental constants. And it doesn't matter about the masses of the black holes. And that number is c to the 5th power over g, Newton's constant. And that number is about in the neighborhood of 100 times the luminosity of the rest of the visible universe. So that's where that comes from. It comes from this basic physics, the size of the black hole, and then how they merge together.
So again, to clarify, Anna, is that it is the power that we are talking about here. It is not energy, because this happens very quickly in the fraction of a second, and therefore the power is large. But if you consider the energy of the rest of the universe, it's way, 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 way more.
Right.
Thank you. So we only have a couple minutes left here. So my last question for you all is there anything you think all of us should know about black holes, maybe about the future of the research, or something that you're particularly excited about that we didn't get a chance to discuss already during today's panel?
I mean, I think the documentary was made before the Event Horizon telescope images came out. And so I thought that would be interesting to mention, was just they talked a bit about the experiment and how they basically constructed all of these different radio telescopes together to make one that's like the size of the Earth. And then they got a really high resolution picture. They looked at the black hole at the center of the Milky Way, and they looked at the black hole at the center of a very big galaxy called M87. And they released the images of the M87 black hole, and it was, the first time that we had kind of a direct image of a black hole. And so I think that was a really cool development that happened since this documentary was made, that they showed sort of animations of what it would look like, but then if you Google, you'll actually see the real images, which look exactly like what they showed, which is pretty cool.
Yes, thank you for mentioning that. I was also really impressed by how close to the real thing it looked like in the documentary, which, as you mentioned, happened before the discovery was actually made. And as was shared in the comments too, if you haven't gotten a chance to watch it yet, I do recommend checking it out after today's talk, because you can definitely learn a whole lot more, and they touch on a lot of different topics that we won't unfortunately have the chance to delve in further today. But thank you. Todd, Smita, anything else that you'd like to add before we sign off?
Just one thing about LIGO was that signal that they talked about, that little chirping sound and that waveform, they did a great job of describing that. And I have to tell everyone here that I get chills every time I think about that. And because for decades and decades, people were trying to detect the signal and working towards doing it. And when we saw that little ringing, it's just profound moments in my scientific life, even though I had nothing to do with it. I just know the people who are working on that. And the same with the EHT, that picture of the black hole event horizon, which is just a staggering thing. And then the last thought I'll leave you with is that it's not hypothetical, in the sense that these time differences that we're talking about and these changes in the warping of space-time are relevant to all of our space missions, all of our satellites, all of our communication technology. So none of this you shouldn't think of basically anything that we've discussed today as being purely theoretical, except maybe the Hawking radiation. Almost everything else we've talked about is well in the bounds of things that have been well tested. So I guess that's how I would end. Smita?
Oh, yeah, nothing more than what Todd and Laura already touched on, I would say. But I just would like to say that we are astronomers, and we always looked at the universe with light, and with LIGO observation, we actually have now a different way of looking at the universe through gravity waves, and whether so it has already actually given us surprises. The masses of the black holes which actually emerge is not something people had really thought that these would be stellar mass black holes, because they're pretty massive, like 30 solar masses or so. It is pretty massive. And so it is surprising. It is most likely going to tell us something more about stars and about how they die, and maybe we'll learn something real astronomical because of these gravity wave observations. Again, I don't work in that sphere at all, but it's just super cool.
Absolutely. Thank you all so much. This was super wonderful, and I really appreciate your time today coming out. And thank you to everyone who gave us your Saturday to come learn about space with us. I'm really glad that we had so many people to participate online, and I look forward to our next outreach event together. So thank you to our panelists, and I hope you all have a great rest of your weekend.
Thank you, Anya. Bye-bye.
Thank you.
Thank you.
Thank you. Bye, everybody.
Bye, everybody.
Bye.